Okay, so one of the great applications of integrating vector-valued functions is solving these problems involving motion of a particle. So here we have the acceleration of a particle given by the vector-valued function that I've written down. And we now are given the initial velocity and want to use that to find the velocity of the particle as a function of t. So the first thing we have to ask ourselves is, well, how are the velocity and the acceleration related? And hopefully you know that all you have to do to get the velocity is take an antiderivative of the acceleration. So we'll write down this acceleration. And all we have to do now is antidifferentiate this thing. So how do we do that? Well, we just antidifferentiate each component separately. And the thing that you have to remember when you do this is that you're treating each component as a separate problem, really. You get a constant every time you integrate, and you get 3 separate constants here, one for each component. Okay, so now we have these 3 constants, and we have to figure out, well, what are they? And this is where the initial velocity comes in. So we know on one hand that this expression that we just wrote down is v of t. So I can plug in t equals 0. And if I do that, I get that v of 0. So when I plug it into the first one, you have to remember e to the 0 is 1. So I get a 4 plus c1. Cosine of 0 is 1 as well, so here I'll get a minus 3 plus c2. And in this last component, I'll just get a c3. So if we plug t equals 0 into what we just wrote down, that's what we get. But we also know that this, from the initial conditions, that this v of 0 is supposed to be 4, 0, 2. So the only way that these 2 expressions can be equal is if we set the components equal to each other. So this tells me that 4 plus c1 is supposed to be equal to 4. Minus 3 plus c2 is supposed to be equal to 0. And c3 is supposed to be equal to 2. So this allows me to say that my c1 is 0. My c2 is 3, and, well, obviously my c3 is equal to 2. So now all we have to do is plug this back into our v of t, and that'll give us exactly what our velocity is. So our v of t is 4 e to the 2t plus 0 minus 3 cosine of 3t plus 3 and 6t squared plus 2t plus 2. And that's our velocity. Okay, so we just found the velocity of this particle, and now the question is, let's find the speed. So how are velocity and speed related? Well, from an intro physics course or from somewhere in your previous calculus experience, you always say that speed is the magnitude of the velocity. And now we legitimately have a vector that we can take the magnitude of. So here, our speed is just going to be the magnitude of the velocity, which is now a slightly more interesting calculation than before because we now have a real vector. So to find the magnitude of any vector, we just take each component, square them, and add them together. That's going to look a little bit messy here, but not really a big deal. I'll write it out just to make sure everyone's on the same page with me. We're not actually going to bother simplifying this at all. So if it were a nicer example, we could do something more with this, but if they don't ask, we can always just leave it as is. So not a hard problem to do at all. What's a little bit more interesting will be the next part where we find the position. Okay, so now we're given an initial position, and we have to find the position function. So how are velocity and position related? Well, to find the position, r of t, all we have to do is integrate the velocity. And as we have written above, the velocity is given by this function. So all we have to do to find the position is going to be to integrate this vector valued function that I just wrote down. Well, how do we integrate a vector valued function? We integrate each component separately. And when we do that, we really have to treat this like 3 separate problems. So when we integrate, we get a constant. We're going to get 3 different constants again. So we integrate that first component and get a 2e to the 2t plus c1. Second component is going to give me a minus sine of 3t plus 3t. And we need another constant, so c2. And the last one, we'll get a 2t cubed plus t squared plus 2t. And we'll have one more constant, which we'll call c3. So we can do the same thing that we did before. This is an expression for r of t. So we now have 2 ways of writing down r of 0. The first way, I can plug in t is equal to 0. And what do I get? Well, r of 0 is 2 plus c1. Sine of 0 is 0, so the second part is just going to give me a c2. And the last part is going to give me a c3. Now, we know from the initial conditions that our r of 0 is supposed to be this vector 5, 0, 1. And so the only way that this can happen is if each of these components are equal. So we get 2 plus c1 is equal to 5, c2 is equal to 0, and c3 is equal to 1. So my c1 here will be 3. I can then write down r of t by just substituting in these values for c1, c2, and c3. So remember, this c1 is going to be 3 from the equation directly above it. c2 is 0, so the second component is just this. And the last component, since c3 is 1, is just 2t cubed plus t squared plus 2t plus 1. So this is not a bad problem at all.